Key discoveries of the James Webb Space Telescope have subverted the case for the theory of the universe's origin. The James Webb Space Telescope has, quite recently, conveyed an outright exhilarating revelation that is sending shock waves through the universe of material science. Through a single amazing picture, it has obliterated long-standing discussions, leaving researchers staggered. The time of theory is over, as Webb's most recent catch is both outwardly spellbinding and a game-changer that vows to alter our view of the real world. What blazing discussion among researchers has this picture unequivocally finished? And in what ways is the dazzling picture caught by the James Webb Space Telescope rethinking how we might interpret the universe? Go along with us as we dig into why James Webb's discoveries are stopping discussions in material science. With a breaking picture, the key issue with astronomy is that researchers can't come to an understanding about how old the universe is or, on the other hand, the way in which quick it is extending. This unanswered peculiarity has baffled researchers across ages, driving them to conduct different examinations to find answers. Cosmology is the field of research that spotlights on getting it, how the universe was made, the way things are set up, and how it has changed over time, and at last, the way that it will end. This field has seen huge advancement in the past 100 years. The currently acknowledged cosmology model, the theory of the Big Bang, proposes that the universe has been growing from a very hot and thick introductory state for about 13.8 billion years. This development is estimated by the Hubble constant, which shows the speed at which the universe is extending. However, estimations of the Hubble constant are not direct. Estimating the Hubble constant can be extensively arranged into two gatherings: neighborhood estimations and early universe estimations. Neighborhood estimations include the investigation of cosmic bodies. For instance, Cepheid variable stars and Type Ia supernovae act as standard candles to gauge the Hubble constant. Because of their splendor, space experts can measure how the universe's development influences the paces of these objects to find their distances and, accordingly, ascertain the Hubble constant. The second gathering is the estimation of the early universe. Researchers use perceptions of the cosmic microwave background (CMB), the afterglow of the Big Bang found during the 1960s. The CMB shows the microwave radiation of the early universe when it was simply 380,000 years old. By estimating the minuscule temperature and polarization variations transmitted by the CMB, astronomers can lay out the age of the universe and its pace of extension. Yet, here's the issue. The aftereffects of these two strategies try not to connect. The outcomes noticed through neighborhood estimations affirm the universe is growing quicker than what we gauge in view of CMB information. Due to these distinctions, researchers have been endeavoring to reveal the reasons behind the outcomes. As such, further research is being directed to learn more about the secrets of the universe. As things stand, the distinction in estimations shows that there is either new science we have close to zero familiarity with or botches in one or the two ways by which we are estimating things. On account of the James Webb Space Telescope, we can see into the dark universe more clearly than at any other time before. The telescope can show the slightest and most far-off components, planets, and systems we wouldn't have thought it was feasible to see. Due to its capacities, researchers normally accepted that information from the JWST would help us in exactly computing the Hubble constant. Anyway, the principal wave of information has astoundingly made matters more muddled. They have given us new insights that are not intelligible with what we assumed we knew. Might this information at some point lead to a new theory and upset how we contemplate space? Provided that this is true, we could have to audit how we might interpret how the universe works. For example, we may find particles and powers that have never been noticed, or it could imply that dark energy, an unexplored world factor liable for the speeding up development of our universe, should be reevaluated. Up until this point, the manners in which we think about space have developed as we proceed to find new things. For instance, in 1965, when analysts found the cosmic microwave background radiation, it filled in as a strong support for the thought of the Big Bang theory. Before then, researchers felt that the universe was everlasting and consequently was continually extending at a uniform rate. Yet, the new proof demonstrated that was not true. Additionally, when we found out towards the end of the 1990s that the universe was ceaselessly growing at an accelerating rate, it further changed our understanding. We found dark energy and its effect on the universe's extension. Thus, Every time we learn something new, we question whether it fits into our ongoing system. If not, we think of new ways to deal with comprehend the universe better. To this end, the issue we are facing in cosmology today could prompt the disclosure of the most magnificent answers for the universe. While the issue is challenging, it is additionally thrilling as it constrains us to foster all the more mechanically progressed apparatuses to investigate space. This cosmological difficulty likewise joins the scientific community from various nations, as each researcher needs to find out about the universe. Above all, it shows that science is continually changing and developing as we get more familiar with space. Alongside the Hubble strain, there is likewise a worry referred to as the S8 pressure. This is as to the spatial appropriation of issue in the universe. This can be utilized to draw a basic image of the universe and perceive how it has developed. Space experts allude to this peculiarity as unevenness because there are areas of space that have parcels of galaxies firmly assembled while other regions are scanty. Researchers will utilize various methods to quantify this unevenness, and one way is to check how out the light from far-off galaxies gets twisted by the different gravity of huge particles, for example, galaxy clusters. This twisting, known as gravitational lensing, furnishes us with a method for examining where dark matter is, given that it is imperceptible as it doesn't emanate light. Scientists likewise utilize the cosmic microwave background, CMB, a phosphorescence from the very outset of the Big Bang. This light has been moving for around 13.8 billion years, bearing news from the early universe. Through CMB investigation, physicists can decipher how the universe was uneven in its introduction to the world, which ought to match the observational unevenness of the universe at the present time on a huge scale. However, here's the catch. These outcomes additionally don't adjust. The CMB's naughtiness introduced by the non-round gravity dispersion model suggests that the matter circulation at the beginning phase of the universe was more homogeneous contrasted with the one noticed involving gravitational lensing. As such, we can figure that there is something different that we are not considering in the clarification. This takes us back to the idea of dark matter. What precisely is dark matter, and how does it work? The truth is the issue remains unanswered. Anyway, all hope is not lost. The James Webb Space Telescope, JWST, is set to reclassify the field of cosmology with its remarkable high resolution and responsiveness. The telescope will analyze early times of the universe and examine the primary galaxies and stars formed. This makes it conceivable to further develop estimations of cosmic extension and matter dissemination. These basic questions will require exact observation and potentially new approaches from a hypothetical point of view to figure them out. Whether or not the end is seeing more significance to dark energy, finding totally new physics, or even acquiring a superior comprehension of dark matter's conduct, the ramifications will be broad. Processing the secrets of the universe is like resolving a zillion-piece puzzle blindfolded. Researchers should be visible as exhaustive investigators who are centered around and fixated on addressing these secrets. The most recent endeavor, called Project Flamingo, is evidence of NASA's increasing energy for logical investigation. Utilizing one of the world's most exceptionally acclaimed supercomputers, arranged at Durham College in England, Project Flamingo is a totally breathtaking accomplishment in the realm of computational advancement. It costs more than 50 million hours of PC time and highlights 30,000 processors and counting. The project features the academic community's resolution to investigate the universe completely, significantly zeroing in on dark matter. Dark matter, the puzzling substance that neither produces, absorbs, nor reflects light, is surmised to exist because of its gravitational impact on noticeable matter. This tricky nature continues to intrigue researchers. However, the methodology of Project Flamingo is unique in relation to past reenactments. It includes all potential types of cosmic components, from galaxies with the most exotic gas content to stars and black holes at the center of the universe. Through such a structured technique, the continuous change in the portrayal of the universe was made from an essential milestone sketch. The inspiration driving aggressive endeavors like Project Flamingo is clear: to explain vast contentions where the estimations appear to be flawed and do not fit into the design of the universe. This dissimilarity in estimation recommends a major misconception in our ongoing understanding of the universe's operations. On the off chance that these measurements could be contrasted with musical classes, They are like jazz and classical, each having its own technique, albeit still related. Flamingo endeavors to join these dissimilar perspectives and hone our individual view of the universe. Anyway, notwithstanding its refinement, the astronomical pressure perseveres. This strain keeps on existing as lowering proof that we presently can't seem to tackle a significant part of the secret that encompasses us. The universe appears to be reluctant to exchange its privileged insights with us. Very much like that, as we add each new piece of information and recreation model to our tool stash like Flamingo and other tools, each new achievement feels like getting one more key piece of the vast riddle. This has brought about a drive to learn and make progress toward a more noteworthy comprehension of the universe. Without a doubt, the universe is covered in mystery, and it can be hazardous to uncover its truths too early. At each insightful step, researchers present refined speculations, altered models, and additional defining requests. The theory placed by the Big Bang Theory was once extremely dubious but is now thought to be an essential part of scientific knowledge today. Similarly, dark matter is now not a speculative thought but an undeniable crucial element of our astronomical riddle. The discovery of dark energy, an unexplored force pushing the universe's expansion, was a late 20th century revelation and is now one of the fundamental essential bits of understanding the universe. Let us now investigate the different ways researchers have attempted to settle the riddle of the universe's expansion through time. They have worked truly hard, yet a portion of the pieces simply haven't made sense. Quite a while ago, it was commonly accepted that each object overhead, from the sun to the stars and all the planets, revolved around the Earth. This geocentric view was challenged by the likes of Copernicus and Galileo, who held that the Earth and other planets moved around the sun, subsequently introducing a revolutionary perspective.